Hello everyone. In this presentation, I will be explaining the concept of different consideration in terms of timing concept as well as inverting and non-inverting type of dynamic shift register. Let me first explain you what are the different considerations we are supposed to take into account while considering the concept of timing. So as we already know, when it comes to the concept of timing, there will be clock phases or clock signals what we are going to apply. So in this particular case, we will be having two distinct clock phases or clock signals. What we will be designating it in terms of clock signal or clock phase phi 1 as well as phi 2. Always when I am using more than one clock signal, I have to assure that the clock signals are non-overlapping in nature. So here we are considering two phases, phi 1 as well as phi 2 clock phases, which should be non-overlapping. Along with that, one should lead the other clock signal. So here phi 1 should lead the clock phase or clock signal phi 2, and you are not using phi 1 and phi 2 for performing the same operations. So whenever I am having the operation of either read or write, so if you consider the memory, the operations which in a memory unit it has to perform, it will be in terms of read operation, write operation, refresh operation and all. So always your read and write operation will be performed based upon the clock signal phi 1, and the refresh operation should be performed at the clock signal phi 2. So phi 1 will be used for performing read as well as write operation, and phi 2 will be used to perform the refresh operation. So that's what I have written over here. So whatever the bits are to be stored, stored means it will be in terms of registers what we are going to make use of. If I want to write something into the register and the subsystem, it should be done only during the clock signal phi 1. And if I want to perform any refresh operation, it has to be done during phi 2 clock signal. And whenever I am applying another clock signal phi 1, at that time the read operation will be performed. So whatever the refresh operation has to be performed after the write operation, it has to be performed before the phi 2 clock signal. So it has to settle before the phi 2 clock signal so that there is no overlapping or no distortion of any sort of data. So apart from that, the last consideration in timing is for a system stability, there must be at least one clock storage element. So here we are discussing in terms of a dynamic memory, that is dynamic storage element. You are having a connection of that particular element in series with every closed loop signal path. So these are the different consideration which we are going to take into account in the performance of timing operation. So we are discussing a storage element here in terms of dynamic shift register stages. So in my next presentation, I will be explaining you in detail how the operation of a dynamic shift register is performed depending upon the number of bits. So in this particular presentation, I will be just telling you a brief description of a dynamic shift register. What are the distinct types of it? So shift register. So registers are nothing but it is used to perform whenever I am going to perform any sort of operation. If I want to store a particular element, either it may be in terms of a data input or a data output, I am supposed to make use of a component called as registers. So shift register means either it is going to perform a right shift operation or it is going to perform a left shift operation. So now in this particular concept, we will be discussing what are the different types of dynamic shift registers. So basically there are two distinct types of dynamic shift registers, one of inverting type, another one of non-inverting type. What is the difference between the two? I am having a particular data input. I have to store that particular data input as it is. Data input in terms of digital logics, if I want to explain, it can accept either the input as equal to logical 0 state or logical 1 state. If I want to store it in the same format, that is 0 and 1 has to be read in the output of the data. That is 0 itself I want in the output and 1 itself I want to get stored in the output. Then I am going to make use of non-inverting type of dynamic shift register element. Non-inverting type of dynamic shift register element. If I want the reverse of this to be stored, if I want the inverted version of this, that is whenever I am having the input applied as 0, it has to yield me the data output, means the data output should read the value of 1, and here 1 is applied as data input and the output should read a value of logical 0 state. In such condition, I want the output in the exact reverse manner, that is inverted version of the input should be your output. In such condition, I will be making use of an inverting type of storage element, that is dynamic shift register element will be used. So now let us see how this particular inverting type as well as non-inverting type of dynamic shift register is going to work. In this case, in the first diagram what you are seeing over here, I am using one NMOS transistor. Along with that, I am having an inverter or a NOT gate cascaded. So here this is the gate input, wherein we will be applying some sort of control signal which will either turn on or turn off a transistor. Suppose if I am applying the clock signal phi as equal to logical 1 state. So this particular NMOS transistor will be turned on. If this is turned on, this is going to behave like a closed switch. If I am replacing it with the help of a switch, it is going to behave like a closed switch. Whatever the data input I am going to apply over here. Say if the input I had applied it as equal to logical 0 state. Since the switch is closed, the entire data input will traverse towards the other side of the transistor. So here also 0 will appear. This 0 is applied as an input for your NOT gate now. So we know the operation or the performance of a NOT gate. When 0 is applied as an input, it will yield as an output of logical 1 state. So now the applied signal was 0 and the obtained output was equal to 1. So it is called as inverting type. If I want, I can check out with application of the input as 1. I will assume this 5 signal as equal to 1 state itself, so that still the clock signal is equal to 1, which is turned on, which has turned on the transistor of NMOSFET, which is behaving like a closed switch. The applied input is equal to logical 1 state. The exact output will appear in case of your logic. So 1 is applied as an input for a inverter or a NOT gate. So obviously it will yield me the value of logical 0 at the output. So we had applied 1 as input and we have obtained 0 as the output. So it is working like an inverting type of dynamic shift register. So if I want the output exactly in the reverse manner to be stored, to be read, then it is called as inverting type. This particular logic we are going to follow it in terms of an NMOS logic. Only NMOS transistor I have used over here. So here I have used NMOS transistor, then cascaded it with the NOT gate. If I am using an NMOS logic, we know how to design an NMOS inverter. So this will be considering one transistor of NMOSFET. To design an NMOS inverter, I require 2 more transistors. So 2 plus 1, in total I require 3 transistors to design an inverting type of dynamic shift register element in case of NMOS design. Now if I want to convert this into a stick diagram, so this is not the exact stick diagram I can call it as, because here the NOT gate I have used it as it is. So it is called a stick plus circuit diagram. So this is the circuit what I have used, that is the logical circuit I have used in terms of a NOT gate. If you want it in terms of an exact stick diagram, then this particular NOT gate should be replaced by an NMOS inverter stick diagram. Means pull up should be a depletion type of NMOSFET and pull down should be a enhanced or enhancement type of NMOS transistor, and I have to take the output from there. So you can just replace this inverter with the help of NMOS inverter, NMOS inverter stick diagram. So if I replace this with NMOS inverter stick diagram, then this entire diagram will be called in terms of stick diagram. Now it is called a stick diagram plus the circuit diagram because it is considering the logical gate of NOT. So now if I want to explain this particular stick diagram, how it is drawn, now. So you know this is a formation of an NMOS transistor, which means that a polysilicon should cross N type of diffusion. So this vertical dotted layer what you are seeing here, it is a polysilicon gate terminal, and this horizontal layer represents a diffusion of N type. So one polysilicon, when it crosses N type of diffusion layer, NMOS transistor is formed. So this is NMOS transistor. Then it is cascaded with an inverter. Then once again this I am going to consider it in terms of a diffusion layer. Further, if I want to make any sort of connection, I can make use of this. If I want it in terms of a pure stick diagram, replace this NOT gate with NMOS inverter stick diagram. NMOS inverter stick diagram means it should be in terms of an NMOS design style, not CMOS inverter stick diagram, but NMOS inverter stick diagram. So this is your circuit plus stick diagram concept. This is what I have explained, how it is going to work like an inverting type. Same way I can make this particular clock signal phi value as equal to 0 state also. If I make this as 0, this transistor is turned off, which is going to behave like an open switch. So none of the data, whether you are going to apply the input as equal to either 0 state or 1 state, it doesn't matter. It won't get passed to the output terminal or output side of this first N MOSFET what you are using. So this is going to work like an inverting type whenever you are going to assert a clock signal of phi as equal to logical 1 state. Accordingly, if you vary it in terms of 0 or 1, exact 0 or 1 will appear towards the output side, and because of the presence of a NOT gate, it will yield the inverted version of the applied input signal. So this is in case of NMOS design. If I want to design in terms of CMOS, complementary metal oxide semiconductor, which is comprising of a P MOSFET as well as N MOSFET. Transmission gate I have used over here, which is nothing but a parallel combination of P MOSFET and N MOSFET. This is your P MOSFET and this is N MOSFET. Again cascade it with an inverter. So once again it is a circuit plus the stick diagram, because this I have not represented in terms of a stick diagram. If you want to represent it, if you want to find all these things in terms of a stick diagram itself, this is anyway stick diagram. CMOS inverter, replace it with CMOS inverter stick diagram, wherein I will be having a polysilicon vertical layer, then two layers of diffusion type, that is PMOS diffusion, P type of diffusion as well as N type of diffusion, and the polysilicon layer you have to cascade it with this particular metal layer, so that it is shown in terms of your stick diagram of a CMOS inverter. So now if I want to explain the operation of this particular logic, again this will also behave like an inverting type of dynamic shift register element itself. But how? You know, transmission gate is capable of passing exact logical 0 state as well as exact logical 1 state. Here I am having the control signal applied for N MOSFET as phi, and complementary version of that is applied to the PMOS control signal. So now let me consider the value of this clock signal as equal to 0 state and this value as equal to logical 1 state. You know 0 is the off condition for N MOSFET, even 1 is the off condition for P MOSFET. Both the transistors are turned off now. When both the transistors are turned off, if I just replace it with the switch, this is an open switch. Even the N MOSFET is going to behave like an open switch itself. So whatever the data, whether I am applying it as a logical 0 state or logical 1 state, it is not finding any of the appropriate path either through the P MOSFET or through the N MOSFET in order to yield you the output over the right side. So I cannot expect any sort of output over here. Usually we will designate it as an high impedance or Z state. So now it is not showing me the exact behavior. Let me explain what happens when I am applying the clock signal, that is phi signal as equal to logical 1 state. So now let me just apply the signal phi as equal to 1. So obviously this phi complement will be equal to a 0 state. It is an on condition for your N MOSFET. Also it is an on condition for your P MOSFET. So this is also a closed switch. Even the P MOSFET is also acting like a closed switch. There is a parallel connection from your P MOSFET to the N MOSFET. So it can take any one of the path. If I apply a logical 0 as an input, either it can traverse through here or it can traverse through your this path. Since it is equal to 0, it obviously takes the path through N MOSFET so that it can yield exact logical 0 state. When 0 state has attained over here, it is behaving like an input for this particular inverter and it will reverse the input. So 1 is the obtained output. 0 was applied input signal and 1 is the obtained output. So now we call this as inverting type. Similarly, if I apply 1, it will take the path through the P MOSFET because P MOSFET is capable of passing exact logical 1 state. 1 is applied as an input to the inverter. So it will yield the output as equal to logical 0 state. So when I am applying the data input as 0, 1 is obtained. When I am applying the data input as 1, 0 output is obtained. So it is called as inverting type. So now how to draw the stick diagram for this particular case. P MOSFET and N MOSFET are connected in parallel, that is transmission gate logic. So I have to consider two layers. Two transistors are present, which means so two polysilicon layers I will consider like this. So hope this is understood. Next, two transistors are supposed to be formed. One of P MOSFET, if I assume this as P MOSFET, I will assume this as N MOSFET. So this blank layer is nothing but a diffusion. So if it is a PMOS, this is P type of diffusion. If this is NMOS, it is an N type of diffusion. How P MOSFET and N MOSFET are connected? In parallel. So I have already told you the parallel connection means the two terminals, either it may be a source or a drain terminal, all the source terminals must be connected together, all the drain terminals must be connected together. So that means it is a parallel combination. So if I assume this as source, if I assume this as drain, if I assume this as drain, and if I assume this terminal as source. So whenever I make a connection of all these drain to drain and this source to source, then it is a parallel connection. So I will just make a connection like this. So it is a different layer because this is a diffusion layer of P type that has to get connected with an N type of diffusion now. So this is a metal layer what I am using and I have to join the drain terminal. Once again I am making use of a contact cut in order to differentiate between the two layers because there are two layers and they have to be connected together. So it is possible only by making use of a contact. So similarly this source as well as this source has to be connected together. So this is your P type of diffusion that has to get connected with N type. So I will be using a contact cut over here and I am connecting it with the metal layer. So this is what is shown over here. So hope you understood how to draw this diagram. So that is how we have drawn the diagram here. Since I have told this particular transistor is a P MOSFET, so the polysilicon, that is control signal, it is marked as phi complement. Similarly, I have marked this as phi complement. This polysilicon I have reserved it for N MOSFET gate terminal or control signal. So obviously for N MOSFET it is assumed as phi here. So this will also be considered as 5. Then as usual, cascade it with an inverter. If you are supposed to draw this in terms of an entire pure stick diagram, then replace this inverter with the help of a stick diagram of a CMOS inverter. So in terms of number of transistor, if I want to explain, the transmission gate what you are seeing over here. So the transmission gate what you are seeing over here, it is constituting of two transistors, one of P MOSFET, one of N MOSFET. So two transistors plus the CMOS inverter will be having two transistors. For one single inverter, there will be two transistors, one of PMOS, another one of NMOS. So 2 plus 2, it will be 4. For this, it is 1 plus 2, which is 3 in number. So for CMOS, it will be occupying more number of space when compared to the NMOS design style. So this is how the inverting type of dynamic shift register element is going to work. Next, we'll see how the non-inverting type of dynamic shift register element works. If I just cascade, if you see this part, this first part, NMOS transistor with a NOT gate, this is an inverting type. If I want to make it as a non-inverting type, I will be cascading it with one more inverting type of dynamic shift register element. Similarly, if you see the transmission gate or the CMOS design style what I have drawn over here, this is the first case what I had explained, that is inverting type. If I cascade it with one more inverting type, then it is going to yield us the output of a non-inverting type. Similarly, in case of your stick as well as the circuit diagram also, if you cascade the first stage with one more of that particular kind, it is an NMOS style. In CMOS, if you cascade the first stage stick diagram plus circuit diagram with another stage of a similar kind, then it is in terms of a non-inverting type of dynamic shift register element. So there is no difficulty in understanding this particular concept if you have understood the inverting type of dynamic shift register element very well. So if I want to explain the working operation of this, once again I am going to consider the value of phi 1 is equal to logical 1 state, so that this will be closed. If I apply it as 0, here the output obtained will also be equal to 0. Here it is an inverter, so when it is passed through an inverter, it will give the reverse, that is 1. Suppose if I make this signal also as equal to 1 in the next cycle, then 1 is going to appear towards the output side of a NMOS transistor second stage. 1 if it is passed through an NMOS inverter, it is going to yield us an output of 0 state. If you see here, I had applied the data input as 0 and I am going to read the value also as equal to logical 0, which is performing this non-inverting operation. Still I am not changing. I am keeping this phi 1 as equal to 1 itself, but I will make the input as equal to 1 state. Now the output from this stage is 1. 1 is passing through the inverter state and it is going to yield us the value as 0. Again phi 2 is not changed, it is equal to 1 itself. It will turn on the transistor of N MOSFET in the second stage and it will pass the 0 in the output state, and that particular 0 element is passed through an inverter and it is going to give us a value of logical 1 state. The applied input was equal to 1, the obtained output is also equal to 1, which is nothing but non-inverting operation. Similarly, if I want to check out in case of your CMOS design, say I will make this as equal to logical 1 state. If phi 1 is 1, obviously phi 1 complement is 0. Both the transistors are the on condition for P MOSFET and N MOSFET. If I apply the input as equal to 0, it will pass through this particular NMOS transistor, so that it will be yielding me the exact logical 0. 0 is passed through an inverter, which means 1 is the obtained output. Again, if I assume the phi 2 signal is 1 and phi 2 complement signal is 0, both will be the on condition turned on. Since it is 1 can pass through this PMOS transistor, so that exact logical 1 state is obtained, and it is passed through an inverter which is going to invert the input and give me the output as equal to logical 0 state. If you compare now, we have applied the input as equal to 0 and we have obtained the output as equal to 0. So exact data input is obtained in the data output. So this particular case we call it as non-inverting type. Let me explain you considering the other case, that is logical 1 state. Phi 1 is 1 itself. So now it will take this particular path because it has to pass pure logical 1 state. So this is logical 1 state obtained. 1 is passed through an inverter, so it will give the output as equal to 0. I will assume this is equal to 1 and again this is equal to 0, because this is equal to 1 means this phi 2 complement should be equal to 0. Next, 0 is passed through this particular NMOS transistor, so that I am getting the exact logical 0 state. It can pass through the PMOS also, but it won't give me exact 0. 0 minus VTP I will be obtaining. 0 is passed through an inverter and it will yield me the output of 1. So I have applied the input as 1 and I have obtained the output value as 1. So which means that if I am just cascading the previous concept, that is inverting type, with one more such stage, then it is going to yield us an output which will be exactly similar to the input what we have applied in the data input. So the stick diagram and circuit diagram is once again carried out from the previous concept itself, that is just cascading of the first stage with the second one. Similarly, this also cascading the first stage with the second one. Here you have to remember this very well. So hope you understood how you are going to have the different types of considerations in the concept of timing. What are the dynamic storage element which we can use? What are the different types of dynamic storage element? What is a register? And what is the difference between inverting type as well as non-inverting type of dynamic register element? So in my next presentation, I will be considering the same concept of dynamic register, but how it can be used in order to perform the shift operation, that is dynamic shift register, considering or in particular with the design for a specific number of bits. Hope you understood this concept. Thank you for listening.